Welcome to today's tutorial. Let's get started. Let's have a look at our agenda for today. Today we're looking at tips and tricks for the Micro OCS's I/O. First we'll review the Micro OCS's built-in inputs. Then we'll look at ways you can apply digital sensors including standard PNP and NPN sensors, as well as open collector NPN and AC. Then we'll look at analog sensors including 4 to 20 mA based sensors, RTDs and 0 to 10 volt thermocouples and load cells, and we'll also look at adding analog isolation. First we'll do a quick review of the Micro OCS on the input side. Every Micro OCS unit from the X2 through the X10 has 12 or 24 volt compatible inputs, and there's 12 of them. They can be used either in positive logic mode or negative logic mode. However, all inputs must be configured the same. On the analog side, you have a choice between 4 to 20 mA input range or 0 to 20 mA input range. You have a resolution of 12 bits. Analog inputs are scaled from 0 to 32,000 counts, but they're in 12-bit resolution, so that means out of those 32,000 counts, you have about 4,000 unique codes. With the Micro X4, X7 and X10, you can also use them with RTD PT100 temperature sensors. The range that we're supporting is from -50 to +200 degrees Celsius. Then the resolution on the RTD inputs is 0.5 degrees Celsius. So remember, for the Micro OCS you have 12 digital inputs and you have 4 analog inputs. Next we'll look at sensors. Let's start on the digital side with PNP and NPN style sensors. The Micro OCS is compatible with both. So what's the difference between those sensors? With a PNP type sensor, you can connect that up so that it's passing the positive DC signal from the sensor into the input pin of the OCS. Then the common connection is made separately. On an NPN sensor, it's the common signal that's being passed from the sensor to the input pin of the OCS. For these sensors, all inputs are configured the same. PNP, also called positive logic, is the most popular. If you look at a PNP sensor, like the PNP sensor in the center, you can see that typically it follows the standard color codes. You have a brown, a black and a blue wire, where the brown is your positive DC, your blue is your common or 0 volts, and your black is your signal wire. The NPN is the same in terms of color codes. In the case of the NPN, the load is between the signal and positive as opposed to between the signal and ground or 0 volts. So those are the standard PNP and NPN sensors. Let's talk about a situation where most of your sensors are PNP but you need to integrate an open collector NPN sensor. This requires an external component called a pull-up resistor. First, on this diagram you see I have an open collector type output device drawn on the left, and I have the OCS input circuitry drawn on the right. Inside that orange box there is a 10K input resistance that's internal to the OCS circuitry. Also connected to the 24 volts at the top in the center is an external 10K pull-up resistor that is something that the user must add. Let's talk about how this works. We'll start with the open collector output being off. Remember, the open collector output is acting as a switch. When the output is off, it's not making a connection between its output pin and 0 volts, so the output pin is open. The circuit flows from 24 volts through the 10K pull-up resistor and then through the 10K internal input impedance on the module and then to ground. That means that the 10K external resistor and the 10K internal resistance effectively are dissipating an equal amount of the 24 volts, or 12 volts each. That results in having 12 volts across the input pins on the OCS, which results in an on because everything over 8 volts effectively is an on. When the open collector output is on, now there is a path between the output pin and a common drawn in red. The signal bypasses the OCS input and goes straight to ground. So that 10K pull-up resistor is going to dissipate the entire 24 volts. Here we need to make sure that we don't exceed the maximum current rating for that open collector device. The maximum current we will run through that switch calculated is 2.4 milliamps. Most open collector outputs can handle up to 10 milliamps. We also need to check the wattage on our pull-up resistor. And when we do that calculation, we can see that's only around 0.06 watts. That means we can use our 1/4 watt or 8 watt resistor as our pull-up resistor with no problem. Here, the OCS input will read as off. Next, let's look at AC. 12 and 24 volt type inputs and voltage levels have dominated machine control applications for safety reasons as well as ease of certification. When you do have AC inputs, you'll often find them on machine retrofit applications. The Micro OCS does not directly support any kind of AC inputs. However, it does support them through the application of a device called an Optoisolator. Let's look at that in more detail. The part of the one we sell at Horner is HE-XACD. So using an external component mounted on a DIN rail, you can convert AC inputs over to DC. Looking at the diagram at the bottom, we'll start with our AC running through a switch and the signal is passed to one side of the Optoisolator. There's also a neutral reference that has to be connected as well on the AC side. Then there's the internals of that device, and then there's a DC side to that device which you connect to the input of the OCS. So overall, this provides isolation and signal conversion between the input signal, which is AC, and the OCS DC input. Now let's begin a demo where we'll look at using that Optoisolator. This is one of these Optoisolator devices. Here's the AC side where we connect our AC signal that we want to detect. This terminal, the A2 terminal, is where we're going to connect a neutral as the reference for A1. Then you have optical isolation here in the center. Then this is our DC side with the positive output pin here and the common output pin. I have one wired up here and I'm using this circuit breaker with a manual switch on it to switch on an AC signal. We have a hot signal running into the top of the circuit breaker down into the Optoisolator. We also have neutral coming into the Optoisolator as well. On the other side we have our DC connections. And then coming out of our DC connections on the other side we have this orange wire that's wired into a digital input. On the Micro OCS in this case it happens to be I1. So if you look at the screen you can see we don't have any power here. So if I turn on the breaker you can see I get an indication both on the Optoisolator itself and on the Micro OCS. With these Optoisolators you use one per AC input that you have. And they're not expensive. Now let's look at analog sensors, starting with 4 to 20 milliamp sensors, which is the most commonly used analog signal. The Micro OCS is compatible with both self-powered and loop-powered sensors. Self-powered sensors have 3 pins, a dedicated pin for you to bring power in and a dedicated pin for the output, whereas a loop-powered sensor is powered from a loop power supply, and therefore it only has 2 pins. A plus lead and then an output or negative lead, and then you wire those up as shown on the right hand side of the slide. The Micro OCS also supports 0 to 20 milliamps. There are other analog sensors that you might want to apply, including temperature sensors. RTDs have become the most popular sensor for this in industrial applications because they're easy to apply, cost effective and accurate. For the Micro OCS, the X4, X7 and X10 models support RTD PT100 sensors. They support from -50 to +250 degrees Celsius. The Micro OCS can support up to 4 RTD channels per system. However, RTD3 and RTD4 share terminals with analog output 1 and analog output 2. So if you're going to be using analog output number 1, then RTD3 is not available. And if you're using analog output number 2, then RTD4 is not available. From a scaling standpoint, the Micro OCS scales the RTD inputs directly into temperature in 20th of a degree Celsius type increments. So if you want to scale the RTD and display it on the screen or use it in your application for Celsius, you just divide the analog input value by 20. For Fahrenheit, you can do the normal Celsius to Fahrenheit conversion, or you can do a longer equation to go straight from the analog input straight to degrees Fahrenheit. Next, let's look at how those RTD sensors could be applied. Here, I'm just simulating an RTD with a resistor. I have a 150 ohm resistor. 150 ohms is right in the range between -50 and 250 degrees Celsius. I have connected that with leads, 1 lead on one side and then 2 leads on the other side, like a 3-lead RTD. Then those are wired directly into one of the analog inputs of the Micro OCS. The wiring isn't that complicated. Here we are scaling our analog input value to temperature. So how do we take our wiring here and convert that to degrees Celsius or Fahrenheit? For that, I'll switch over to Cscape and show you some simple logic to do that. This is the first rung where I'm doing my scaling for my RTD. First, I'm taking the analog input value which is coming in from the second analog input into a variable called RTD raw integer. Then I'm converting that over to a real variable with a similar name called RTD raw real. Then I divide that by 20, giving me my value in degrees Celsius. Now to get it into Fahrenheit, I just did a degrees Celsius to degrees Fahrenheit conversion using a math expression block. That's one way of doing RTD temperature scaling. Next, let's look at different types of sensors including 0 to 10 volts, thermocouples and load cells. Many other sensor types can be used with the Micro OCS, but simply require an external transmitter. These are available in a variety of different shapes, sizes and price ranges, as you can see on the right. These transmitters convert to 4 to 20 milliamps, allowing direct connection to the Micro OCS. You can get ones that are DIN rail mounted, and you can get thermocouple and RTD transmitters that mount right inside the thermowell. You can get these transmitters from many different companies. Okay, let me show you one of those transmitters in action. Today I'll be using one from a company called Novus, which are based in Brazil but have distributors in Europe. This is a universal transmitter that can be configured for many different sensor types such as thermocouples, RTDs, 0 to 10 volts, load cells, etc. And it also allows you to narrow down the range for that sensor strictly down to the range that you're using. As I mentioned, there are many different companies that sell these transmitters, and this is just the one I'll use for our demonstration today. So now let's begin that demonstration where I'll be showing you how to use that universal transmitter. Here is my universal transmitter. So I'm using a simulator device to simulate a 0 to 10 volt signal. Right now it's showing about 6 volts. So I'll go back and show the transmitter screen. What's happening here is I have a 0 to 10 volt signal flowing from my sensor which I'm simulating into the transmitter, and then a 4 to 20 milliamp signal running from the transmitter into one of the analog inputs of the OCS, and I have the signal path displayed there at the top. The OCS does the A to D conversion, and that scales from 0 to 32,000 counts. And then we use logic to scale into engineering units. In this case, I'm showing both the raw number of counts as well as the engineering units. Here, my engineering units that I'm simulating is 0 to 30 psig. So as I increase the voltage of the input signal, my pressure reading increases up to the maximum. So now let's go into Cscape and see what our scaling looks like. In my second rung here, I'm doing the scaling for this transmitter connection. I start with the straight analog input. I have a variable that's mapped to AI1, then I'm converting that to a real variable. Then I'm scaling 0 to 32,000 counts coming in to 0 to 30 going out, which gives me my psig. That's all I have to do here. Next, let's talk about isolation. The Micro OCS analog I/O is non-isolated because of cost limitations. Isolated analog I/O is quite a bit more expensive and takes up a lot more space physically than non-isolated I/O. But there's only certain situations when you actually need isolation. For example, you have an application where there's the potential that high voltage could be applied to the analog signal path during a failure of some sort. Another situation where you might need isolation is if you have ground loop issues. For example, is there potential voltage differences between where your sensors are installed and where your instrumentation is installed? If that's the case, again you can consider adding isolation. If you do want to add isolation, maybe just for one signal or one thermocouple for example, you can add either an isolated transmitter like the one I showed in our demo, or if it's a 4 to 20 milliamp signal, you can use what's called a loop isolator. That doesn't necessarily convert the signal, however it does isolate the external 4 to 20 milliamp loop from the 4 to 20 milliamp loop that's connected to the Horner OCS in this case. Thank you for joining us for today's tutorial, and the Q&A session will begin shortly.